Hello everyone. This class is going to be on axiom of choice, which is like this very seemingly very innocent result. It's essentially saying like if you have a set S, right, and all the elements of S are also sets. So like I don't know, S1. I'm probably assuming countably many in this case, but so each of the SI is a set. And the axiom of choice, I'll call it AC for short. It states that, let's call this X actually. Given a non-empty collection X of non-empty sets, you can choose an element from each set. That's all it states. It's not anything complicated. It's literally just this. So this leads to like very weird results. For example, some of you may have heard of the Banach-Tarski paradox. It states that if you have a sphere, a solid sphere of some radius, then you can split it into finitely many parts, in fact, I think 4, and you can rearrange it such that it now forms 2 spheres of the same radius and both solid, which basically makes no sense. And we'll intuitively. And we'll also look at a lot of problems that seem very counterintuitive, but can be proved with the axiom of choice. But like before we get to all of that, I'll just define stuff because infinities are pretty weird things. So that would like probably just a famous thing. Let's consider 2 sets. One contains all the natural numbers and one contains all the even numbers. Which of these has more numbers? Any guesses?
Both are same.
Yes, both are same because you have this sort of bijection from like X in the first set to 2X in the second set. So you can pair up 1 with 2, 2 with 4, 3 with 6, and so on. So this is also how we are going to say that 2 sets have equal cardinality. For infinite sets, for finite sets, it's obvious what the cardinality is, but we'll say they have equal cardinality if there exists a bijection between the sets. Like basically, you can pair one element from one set with another element, another set with no repeats. And it's the same thing, like this number is called Aleph naught. That's probably not how Aleph looks, but it looks more like a chi, but you get the idea. So like basically a lot of things have this. For example, the set of primes. This also has the same cardinality because primes are infinite and you can order the primes P1, P2, P3, and so on. And so you can just create this bijection again. So if there's an infinite number of elements, but it has the same cardinality as the natural numbers, then that set is said to be countably infinite. And also the number of rational numbers is also countably infinite. You can show that. It's not too hard. But then we come to the real numbers, which is like, I can't even write it. It's just like every real number from minus infinity to infinity, not included. So this can be shown to have a greater cardinality than n. The classic proof is Cantor's diagonalization proof, where he basically says, do we use fairy numbers for rational? Yeah, I guess you could do that, but also you could just message to everyone because everyone can see what you're saying there. Like, I think an easier proof would just be to like say a rational number corresponds to like some pair of natural numbers and like a natural number. So it's like n squared. So really you want to show that the number of points in the plane is countable, but this is just true because you just enumerate them like this. I mean, the number of lattice points in the plane, not every point. But yeah, it can be done. You can do it as an exercise. I'm mostly skipping over these things because it's not that important. But if anything just makes no sense, if you have a question, feel free to ask. So yes, the diagonalization proof goes like, suppose there exists some sort of bijection between the natural numbers and the real numbers, right? So, and real numbers we'll only consider between 0 and 1. It can't be more than real numbers everywhere. In fact, they're equal. So like, suppose the number you get is like, I don't know, in base 10, it looks like this, and random stuff. And maybe it just even terminates, in which case we'll just let the rest be zeros. So what you do is, first you go through the first one, first place, we'll start with 0 point. And then we look at the first number and the first digit after the decimal. It's 1. So we'll pick something different, say 2. In this case, we look at the second decimal digit of the second thing and it's 1. So we just pick something different, I don't know, say 5. And the third decimal digit of the third number is 6. So we just pick something different, maybe 5 again. And we just keep repeating this and we get some number, which is also between 0 and 1. But at the nth place, it differs from the nth number on this list because of how we created it. Therefore, it cannot be. There's like obviously the slight problem of like 0.99999 being equal to 1.000. But you can just choose the number so that it doesn't happen like this. So yes, there are more real numbers than natural numbers for some definition of more. So the axiom of choice, the only problems that arise in it are the problems I'm claiming are when something unintuitive comes up. These kinds of stuff just happens when you try to use the axiom of choice on uncountable collections of sets. There's something called the axiom of countable choice, which essentially lets you ignore all of the crazy stuff that the axiom of choice causes, but also allows you to have all the results you want from the axiom of choice. So the axiom of choice is also pretty cool. And an important thing to note is that in the axiom of choice, the reason it's necessary is because you're arbitrarily choosing an element from each set. If suppose your sets were like, say, the set X is the set of all subsets of natural numbers, that's uncountable. So like it contains, say, all singletons and so on. It also contains all pairs of stuff. And it also contains like infinite. It's a set. It contains n itself and so on. So like this is a pretty big set. But now what you could say is that you can just say pick smallest element of each subset. And in this case, you're actually specifying which element you want to pick. So I chose natural numbers so that there does exist the smallest element of each subset. So the point is, in this case, there's no choice that you need to make, and hence it's called the axiom of choice. Because in the axiom of choice, you're saying arbitrarily pick an element from each set. Whereas here, what you're saying is you're giving a definite rule. So given any subset, there is a fixed thing that must be picked. There's like no randomness in this. And to do such a thing, you do not require the axiom of choice. The axiom of choice only comes relevant when you're doing weird stuff and just picking randomly. And note that if X was instead subsets of real numbers, this would not be valid because a set does not have to have the smallest element. Does that make sense? Yes. Okay, nice. Okay, what next? Okay, so the first problem we're going to do actually sounds extremely stupid. And it's also not particularly interesting, but I think it does have some instructive value. So we'll actually do it. Show that every infinite set has a countably infinite subset. If my handwriting is unreadable, like do tell. I do not have the greatest handwriting by any means. So yeah, think about how you might do such a thing. And I agree, it does seem like a stupidly obvious statement, but you actually can't show this without the axiom of choice, which is pretty weird. So think about it. So any ideas, like even if it sounds silly, just say it. Because there is a very obvious sounding thing that seems like it should work. Okay, I'll assume none of you have ideas. So
You can
the
just
obvious thing I can think of was just like, just pick an element from the set and we'll just remove that element from the set, then pick another element. Just keep repeating this. And you have a countably infinite subset because you're picking like in the first turn, the second turn, and so on. What does countably infinite mean? It means it has cardinality equal to that of the natural numbers. It basically says it's an infinite set and you can order the elements like 1, 2, 3, 4, 5, 6, and so on. So the obvious thing is to just say in the first turn, just pick some element, say x1, then pick an element x2, then pick an element x3, pick an element x4, and so on. And there we have a countably infinite subset. But there is a problem with that. The problem is that you're kind of doing this inductively. So like you have like n minus 1 elements already, and you're just picking another element. So like at any point, you still have a finite number of elements chosen. Like after a billion steps, you still have only a billion numbers. So you can create arbitrarily large finite subsets, but you can't actually create an infinite subset like this. So it's kind of hard to see and it takes time to get used to, but this only shows it for all natural numbers that you can find a subset with those many elements. It doesn't show that there is an countably infinite subset.
I have an idea. So like that power set idea thingy, like you consider the power set of the set you have,
Okay.
and you can just like from like power set is the set of subsets. Like you take each subset, you take any element from the subset at random, and you consider the set of those elements. So like let's
Yes.
say we picked xi in some power set. So like there will be subsets which do not have xi. So we'll be able to pick other elements also. So at times, suppose we have like n elements, and then there will be a subset not containing any of those n elements.
Yes.
So, and this will guarantee infinite elements and
Yes,
counting.
to write it formally, also the axiom of choice formally, it states that given any set X, a, a collection of sets X, exists a choice function, which is defined as f of s, such that f of s is s for all sets s and x. So yes, as Pranav said, you do consider the power set of the set you have. The point is just that you have a lot of subsets, and then you can actually use the axiom of choice. So by the axiom of choice, we know that a choice function exists. So to write it more rigorously, like set g of 1 to be, I don't know, let's say f of s. And then for define g of 1 to be f of, what am I doing? S excluding g of 1, g of 2, all the way till g of n minus 1. So at first glance, this seems like it's nothing really different from what we did earlier. Like earlier also, what we did was, well, we were just picking elements. But the point is, in this case, you don't have to arbitrarily pick an element. The axiom of choice already has done that for you by assigning like an element to each subset. So over here, G is actually well defined for every natural number. But if you try to like write up what we did initially formally, you can't really do that because you're essentially saying arbitrarily pick an element from S excluding those, which is not possible without the axiom of choice. But does that make sense?
I have a doubt in the like formal definition of axiom of choice. Like, what does f of s belong to s mean? Here?
Like F is a function that takes in a set and outputs some element.
Oh, okay, got it.
So for every set in X, it assigns it some element inside S itself. And that's called a choice function because math people like to be fancy.
Are all the choices distinct?
Sorry?
Are all the choices distinct? I mean,
Yes. So because we're defining G of n this way, we are excluding, change this to be, we are excluding all of the previous choices here. So there will not be repeats. Thank you for pointing that out. That is important. Otherwise, you could just pick the same element infinitely many times. So, okay, that wasn't really the most interesting example. Let's actually get to the weird part. So there are a lot of norms. Yes, it's quite weird actually because it feels like just pick elements, what more do you want? But it doesn't work, which is kind of counterintuitive, but it's not remotely as counterintuitive as the crazy stuff we're going to do now. So there are a bunch of norms that like weird imaginary creatures that exist in gardens, or so I understand. They're just for the flavor text. You don't actually need them. So like, let's call them G1, G2. There's like countably many of them. And there are a lot of hats. So like, and hats come in also infinitely many colors. Say C1, C2, C3, and so on. So these gnomes are allowed to come up with any strategy they feel like beforehand. And then they all close their eyes. And then like some magic creature, let's assume, gives each of them a hat of some color. So then the gnomes open their eyes and they can see the hat of every person except their own because like they can't really like look up, let's assume. So, and then each gnome has to guess what color hat they're wearing. So prove that there exists a strategy so that only finitely many gnomes spell. guess wrongly.
Are they guessing the color of their own hat?
Sorry?
Are they guessing the color of their own hat?
Yes, they are guessing the color of their own.
Can't they just see the color of a hat of every gnome existing and then guess?
There is not necessarily one hat of each color. There can be multiple hats of some color,
Oh, okay.
maybe some color there are no hats.
Okay, that's it.
So like just seeing everyone else's does not actually give you any information. Like any information that you can directly guess. And also like any such strategy cannot actually be described.
Okay,
You
how
just know
about
that exists.
uh, like they can discuss in the beginning, right?
They can discuss in the beginning.
So what if like they decide that whatever which does, uh, they can like order among themselves, and no one will say the hat color of gnome 2. Like no one will say the hat color on an
So
NPC.
all gnomes guess simultaneously.
Oh, okay.
They're not allowed to pass on information,
I see.
which makes it pretty weird that the statement is true. Yeah, think about it, but it's a pretty non-standard idea, which if you haven't seen these kinds of things before, I don't think it's actually obvious at all. Oh yes, I completely forgot. Turn on videos, people. It's a lot more interesting then. Otherwise, I just sound like a brain dead person. The number of gnomes is infinite. The number of colors is also infinite. Or it can be finite. It does not matter for the purpose of the problem. Yes, thank you. I have at least one person with video. It's fine to those of you messaging. I'm not judging your haircut, so like, it's fine. Switch on video. Kind of excuses are these? In school, people have better excuses. The 100 green hat.
Yeah, I think there was some problem like this in like a puzzle book or something with norms and hats.
Ah.
I don't remember.
Also, assume that gnomes are like very smart and they have like infinite memory or something. You think surely did? Oh, that one, the island people. Yes, that is so cool. I still have. That is also very disturbing and real.
Which problem?
Yes, induction solves it, but is it the correct answer? Is there even a correct answer to it? But yes, we will not get distracted by other interesting problems. We must only do stuff based on the axiom of choice because that's what this class is. Okay, so the idea is the following. So we consider like let X be the set of all sequences of natural numbers, all infinite sequences of natural numbers. So like everything being one is valid. like I don't know, 1, 2, 1, and then 1 always is valid. You can have 1, 2, 1, 2. That's also valid. You can also have like 1, 2, 1, 1, 2, 1, 1, 1, 2, like not even periodic. That's also valid. Like any infinite sequence of natural numbers, we're going to let x be this. We're actually not going to let x. But fine, whatever. So, but now the very clever part is, let's say that two elements of this set X, say X1 and X2, we're going to define an equivalence relation where X1, what is this called? X1 is related to X2.
Tilde.
What?
It's called tilde. No?
It's called what?
TILDA.
TILDE or E. Okay, not the point. But I'll just say related to. If and only if X1 and X2 differ in finitely many places. So you can check that this is an equivalence relation, because obviously everything is related to itself because they differ in 0 places. And if A is related to B, then the different finitely many places, so B is related to A too. And if A is related to B, B is related to C, because finite plus finite is finite. You also have A related to C. So this is actually an equivalence relation. So the point is, this splits it into a bunch of equivalence classes, C1, C. I should not use 1, 2, 3 as the indices because these are uncountably many, but for some abuse of notation. So it splits it into these equivalence classes, where in each class, every two numbers differ by finitely many places. So what we're going to do is we're going to let some, let's call this X dash to be the set of all equivalence classes. And we're going to, by the axiom of choice, isn't an easier way to say? Yes, you could also call this relation as that after sufficiently many places, both of them are the same sequence. So we're going to, by the axiom of choice, obviously, we can pick an element from each of these things, right? And we'll just like call f of ci as the representative of that class. So the point is, when the gnome opens its eyes, it sees like everyone's hat except itself. So if it considers and also we assume there are countably many gnomes. So G1, G2, G3, G4, this is that. So suppose we're considering gnome 3. So what he does is he sees what color gnome 1 is wearing, say CA, or gnome 2 is wearing C1. He doesn't know what he is wearing, but he knows what he's wearing, C5. And so you get some sequence, an infinite sequence of natural numbers. And he doesn't know what himself is. Let's assume he assumes he's 1. So what he's actually going to do is consider this sequence. And because of the equivalence class thing, it lies in some equivalence class, say Cj. And note that all of the gnomes are going to think of the same equivalence class Cj because they all differ by finitely many places. In fact, 2 at most. So the advantage of this is that every gnome, when they see this, they're just going to assume that the actual sequence is actually f of Cj. Like even if they can see it's actually not, they just assume it's going to be f of Cj, and they just, so gnome I just guesses the ith place of f of Cj.
How is f of Cj defined again?
F is the choice function. So X is the set of all these equivalence classes. So by the axiom of choice, you can just pick one representative from each class.
So like norm I will pick like the representative of this thing.
Yes, every gnome is going to pick the representative of this.
So like
And
every
that
norm will
can,
pick same thing basically.
yeah, everyone assumes it's the same sequence.
No, they're assuming the same sequence. That's fine. And you are saying they pick, like, let's say the sequence is Cj. So they pick f of Cj, which
Yes.
is basically a fixed number, right?
No, like f of Cj is an infinite sequence because Cj is a collection of infinite sequences. F of Cj is just like one such infinite sequence among them.
Okay, got it.
So essentially, each of them, gnome I guesses the ith place of f of Cj. And because f of Cj differs from the actual thing in at most finitely many places, because of how the equivalence class was defined, we have that only finitely many gnomes will guess incorrectly. So at what point did we actually use the axiom of choice?
To pick the representative.
Yes. So like, if I just said like pick a number from each of these classes, it would have probably sounded believable. But the problem is there are uncountably many, so you actually need the axiom of choice to do this. And without the axiom of choice, you actually can't. So something that kind of sounds obvious that, just pick a element from each class, you actually can't do that without the axiom of choice. And if you assume the axiom of choice, you can do this, and you actually get this pretty weird result. Yeah.
Why can't you do that without axiom of choice?
How do you do it without axiom of choice?
Like I trade through each of those sets and pick it.
You iterate through each of those sets. There are uncountably many such sets. How do you iterate through them? You can't order them anymore.
So like, okay, each norm sees a sequence, right?
Yes.
You can just, oh right, they cannot fix the sequence that way. Like,
Yeah.
okay.
How do the norms decide equivalence class? So they can see every other norm. So they essentially know, let's call this the actual sequence. So I don't know, let's call it ACT, which also stands for Allen Common Test, but no. So yes, so they can see all elements of the actual sequence except one, which is their position. So they can see the actual sequence, and the actual sequence is, yeah, they can see all but one place. So, they can just assume their thing is one to just fill the gap. And then they look at which class this entire sequence is in. And because what every gnome sees, so like say gnome 2 sees, actually, oh, so I'd actually guess right. That's not good. And let's say this guy actually was color 5. And this gnome can't see himself, so he guesses 1. And like both are same after that. So this is what gnome 3 says, and this is what gnome 3 sees, and this is what gnome 5 sees. And because they differ in at most finitely many places, in fact at most 2, they are in the same equivalence class. Infinite. Yes, like in fact, even more than infinite computational power. They have infinite memory. They're supposed to remember like what you are choosing for every equivalence class. So yes, like not very realistic, but we're assuming like gnomes are better than humans, which they very well might be. Okay, so let's just do an example. Except there are infinitely many elements, so I'm not sure how I'm supposed to give this example. Let's say, okay, let's just assume that the gnomes have had colors, let's say G1, G2, G3. Then they have, say, C3, C7, C8, C6. And by some interesting luck, it actually repeats. Like just say C3, C7, C8, C6, C3, C7, C8, C6, and so on. So Gnome 1, he doesn't know what the first element is, but he then knows that it's 7, 8, 6, 7, 8, 6, 3, 7, 8, 6, 3, 7, 8, 6, and he doesn't know what the first place is, so he just assumes it's 1. The second guy, he guesses like this. I mean, this is what he sees, it's not what he guesses. Imagine not using G6. Yes. So this is what Gnome 1 sees. It's an infinite sequence. This is what Gnome 2 sees. This is what Gnome 3 sees. And all of these lie in the same equivalence class because any two of these differ in at most finitely many places. In fact, at most two. Therefore, they all lie in the same class. So they all correspond to some same class CJ, which there's no really good way to describe CJ. It's just the set of all sequences of natural numbers that differ from this in at most finitely many places. And let's just suppose that the representative for this chosen was like 9, 9, 9, 9, 9, 9. After that, 8, 6, 3, 7, 8, 6, 3, 7. Like maybe this is, oh God, what happened? There. So suppose this is f of Cj. It's clearly in Cj because it differs from any of these by finitely many places. We can say yes, but when I said sequence, I assumed that everything had a natural number. We need difference, what?
Oh, the sequence I said is just the same as what the nodes had. So that it's the same sequence, not equivalent.
Ah, okay. And same sequences are also in the same equivalence class. To just clarify that. So the gnome is just going to assume that this is this, even if they can obviously see, such that in this case, he knows that the first guy is having color 3 hat, but following the strategy, he just assumes that the first guy has a color 9 hat. And he assumes that he has color 9 too. But the point is because it's in the same equivalence class, like f of Cj and the actual thing, they're both in the same equivalence class. So they differ in at most finitely many places. So beyond the point, every gnome will actually end up guessing correctly. Does that make sense?
Yes.
Okay. See, that's an interesting problem. So the last problem I wanted to do, I'll actually leave it for the end because it's a very crazy sounding thing. And it's also something I sent on the OMC server. So I'll actually even give the statement at the end. But apart from the axiom of choice, so I think it's also pretty important to know what you can do and what you can't do when dealing with infinite things. And I also want to mention like this scam thing that actually ends up working most of the time, although you do need to be pretty careful. So yes, axiom of choice was clickbait. I'm actually not doing axiom of choice. So let's actually do this problem because this solution is pretty fun. Prove that there exists a set S of integers such that for every arithmetic progression, there is an S, there exists two element x1 and x2 in that AP, such that x1 is in S and x2 is not in S. Essentially, like it intersects every AP and its complement. And this does not require axiom of choice or anything, so don't worry about that. There's like a normal solution that exists, and there's also the funny solution. So yeah, think about it.
Can you please explain the question again?
Sorry, could you repeat?
Can you please explain the problem again?
So prove that there is an infinite set S of integers such that for any arithmetic progression you pick, there is some element of the AP in the set, and there's also some element of the AP not in the set. So you just need to prove that there exists such a set of integers. You can describe such a set, but you don't need to.
In this, my idea is that for any integer a, then we consider all integers that are congruent to b modulo a. Then this class of integers that are congruent to b modulo a, they are neither disjoint nor contained in S.
Yes. That's actually kind of similar to the scam solution. It's not really a scam, it's a valid solution. But yes, in this case, it turns out that it is kind of easy to describe it in a more sane way. So yes, actually, let's just show it as I've said. So every arithmetic progression can be just described as the set of X such that X is congruent to A mod B. So we actually just, for every integer, we'll start with say 2, I don't know, or 1. So we first look at stuff with this block. So we are going to actually build S and S dash, S, the complement of S, like N minus S. So what we're going to do is first we look at X is congruent to 0 mod 2. And we just pick one element of this and place it in S.
By the way, shouldn't S dash be Z minus S?
Z, yes, of course. Yes. Is that how it's written? Yes. So we'll pick one element like this and place it in S. And we'll pick one element of this and place it here. Next, we'll look at X is congruent to 1 mod 2. We'll take one element that hasn't been chosen already. You can do this. And then place one here also. Does that mean the AP consists of some integers and some fractions? Yes. Assume that the AP has integer common difference in starting term. Although that's not even, it's fine, yeah. Even if that's not the case. But then you'll just pick a random AP like 0, root 2, 2, root 2. Yeah, fine. Assume the common difference is in integer. So yeah, the idea is next you just do the same for X is 0 mod 3, X is 1 mod 3, and X is 2 mod 3. Just pick some element here, put some element here. And like this, you can just do this. And it's countable, is the point. Because you're doing this for at most like n square things, because you first choose what it's modulo and then you choose the residue. So it's like just a pair. So such a thing is countable. And you don't need the axiom of choice or any such thing for this. So like just for a concrete example, like say X, we're looking at X is 0 mod 2, or we just place say 0 here, and we place 2 over here. Then we look at X is 1 mod 2, and we place say 3 here and 1 here, because why not? Then we look at x is 0 mod 3. 0 and 3 are already here, so we won't place them. Instead, we'll place a minus 3. And then x is 0 mod 3 over here. We can just put 6. X is 1 mod 3, something like this. And you can keep repeating like this. And that just actually just works. But actually, a simpler way to do this would actually be like, let alpha be irrational. Take S to be the set of like integer part of an alpha. And you can show this one. I think this was what the intended solution was. But yeah, you can also just do it this way.
How is the irrational solution easier? Like, who thinks of defining irrational numbers when the question is only about
It
integers?
sounds reasonable. Like,
The first one is reasonable. Like, you won't think of defining an irrational number when it's all.
like the point is, this is kind of an AP, but an irrational AP, kind of. So it actually ends up picking numbers in no particular order. Essentially, like intuitively, like obviously there is another, but intuitively, it for any AP you pick, it can't really match this, or it can't really like anti-match this, if that makes sense. So like it probably does intersect every, and it does.
Like, how do you show that it intersects every AP?
Like pick say root 2.
Huh.
So suppose you want to show it intersects every AP. Suppose it doesn't. Like you just want to show that if you can find something like x is congruent to A mod D, you can also, or just look at like fractional part of this thing, and fractional part plus integer part of root m
Isn't the
mod
first
D.
thing just 0?
There is no integer.
Uh, how do you take modulo of? Oh, hmm,
That
okay.
like it's just a number from 0 to p minus p, from 0 to p, and you just want to show that it goes through every thing interval from like 1 to 2, 2 to 3, 3 to 4 and all. And this you can just show by PHP. We will not do it because this is the boring solution. The cool kids do this. You just order everything and just randomly do stuff. You don't care. So, okay, another example. This is probably going to be a bit more fun, especially because there is a possible fake solve. So, 5-1. Okay, let's not draw this. Yes, so there you're given a set L of lines in the plane. Right. So prove that there exists a set P of points, of lattice points, lattice line, uh, such that for all lines in L, there are exactly 2022 points of P on L.
So in this, we will call a line full if it already has 2022 points in it, and we will call one vacant if it does not have 2022 points in it. So for any line that is vacant, we take a lattice point that does not lie on any full line, and then we add it to P.
Yes, that's exactly the solution. Nice. So obviously the number of lattice lines are countable. So L is also countable. So we can do such a thing. So just order the lines, say L1, L2, and L3. And to use what Arif said, if we'll call a line L full, if it has 2022 points, and vacant otherwise. So inductively do the following thing. Suppose you've done stuff so that all of L1 till Ln minus 1 are full. Then we look at line Ln. It looks like this. And because it's a lattice line, it has infinitely many lattice points. So what we're going to do is we're going to pick a lattice point that hasn't been chosen already. And we're going to pick, if there are k points on Ln so far, we're going to pick like 2022 minus k points. Lying on line Ln, but not lying on any of the other lines.
Any of the other full lines, right?
Sorry?
Any of the other full lines, right?
Any of the other full lines.
Yeah, because like I think it's not possible to pick like
Yes, because if you just pick L to be the set of every possible line, then that's not true. Yeah. So the reason we can do this, and the reason we're doing this is because what if there is some other line, like say Ln plus 1000, which actually had 2021 points picked already, while picking L1 till Ln minus 1. Actually, assume there was a line that was already full, and now you happen to pick their intersection. So now this future line becomes like extra full or something. So when you reach that point, you actually want to kind of delete that point. So to avoid this, and this is in fact also the fake solve we'll look at, because it is very easy to just say that, but it does not work. So we must do what Arif said. You pick it such that it doesn't lie on any of the full lines. And you can do this because there are only finitely many full lines, because like there have been at most like 2022 times n minus 1 lines marked, and any full line has like 2022 things. So it must contain at least 2022. So you can have at most these many lines, which are full already. It's a weak bound. The point is it's finite. So because this has infinitely many points, you can actually choose a point like that. And by induction, we are actually done. So observe the difference between this and when we were proving that thing where it said, prove that every infinite set has a countably infinite subset, because over there we were picking stuff randomly. But here it's like well-defined which point you're going to pick. Because you could just like, over here, I agree, I'm saying arbitrarily, but you can say like, pick the point on these lines closest to the origin that is not part of any full line. And that's like a valid definition. And there's no actual randomness involved. So you don't have to involve any axioms of choice and stuff. But let's actually look at the fake solves, because fake solves are more funny to look at than actual problems. So suppose we ignore the condition that we're actually going to pick such that it doesn't lie on any full lines. And instead we just say that pick any point on this line that doesn't appear in any of the previous n-1 lines. And that sounds like it should work too. Like the only problem is that you might have some lines that end up having more than 2022 points at some point in the future. Because as I pointed out, if you have like say n plus 1,000 and it already was full, and you just chose another new point here, then it's now like overflowing or whatever you want to call it. And
We won't be able to choose that in your strategy, right? Because like the way we are doing is like, let's say when we are at n plus 1,000, we just
yeah,
see how many more points we need first, and then we remove all the lines which intersect it and are full, right?
yes. So I'm saying if you forget to do that and you just say pick any point on this line that hasn't appeared on any of the previous n-1 lines, you don't bother about the full thing.
Oh, then in the future it might occur.
Yes, but this seems fixable because you can just say that if a line is overfull, then for each extra point that you have, just delete it and replace it with a corresponding thing on whatever line you deleted it from. And that sounds like it should work. But now there is a problem. So let's actually define the sets after n turns. So let's say S1, S2. Can we have more than 2022 points? Like the way the strategy works, it ensures that no line has more than 2022 points. But if your question is 2022 special? No, it can be replaced with any number. It can be replaced with any number more than 2022 too. So yes, we're going to look at these sets. And these sets are going to be like subsets. It's a bit weird, but bear with me. Where the first subset here, we're going to make columns also. The first set is going to be the set of all points chosen on L1, right? So let's say some point A1, A2, and maybe there was some A3 chosen on L3. And A1, A2, you get the point. Maybe you added A4 now. So in the first thing, you're not actually deleting any points. So we actually have that Si is a subset of Si plus 1, where I'm assuming like this is a subset of this. Some abuse of notation, but you get the point. Or, okay, let's not even make this that complicated. Let's just define S is the set of all points chosen after one turn, 1 minute or something. Let's assume you can do one thing per minute. Why not? And then the same thing, but 2 minutes. And so on. So what I mentioned earlier, it holds here too. Induction doesn't prove anything for infinite things. It only proves stuff for arbitrarily large things. So what we're essentially doing here, so we are claiming that as n tends to infinity, like this limit is well defined. That's what we're saying. And in this case, that is actually correct because in the first strategy that we were doing, S1 is actually a subset of S2, is a subset of S3, is a subset of S4, is a subset of S5, and so on. And once you choose a point to be in the set, you don't remove it. So like if I just ask, let's define this to be S infinity. If I ask, is a point in S infinity or not, you can give me a straight answer. If it's after some number of turns, it's in one of the sets, then you know that it is in S infinity. S infinity doesn't exist. It's just what we're considering the limit to be, because we do need some final thing. So the problem in the second thing is that you're actually being allowed to delete points, because you're like, oh, if my line has too many points, let me delete some and replace them with something else. So all of these sets, S1, S2, S3, and so on, all exist. But the problem is this is not necessarily true anymore. And if I ask you, is a point in S infinity or not, you can't give me an answer directly. Because even if it's added at some point, it's possible that in the future, it has to be removed. Does that make sense? So S infinity is actually not well defined in the second case. So that is actually not a valid solution. Does that make sense? Kind of. Like if it's weird or something, just I'll repeat stuff. I can't decide if this is repeat or not. Okay, I'll just say it again because I think it's pretty weird. So what induction does, as I mentioned, is it only proves stuff for arbitrarily large things. But we technically want S infinity because you want to know what happens after infinitely many steps. But induction doesn't really do that. So we're kind of defining the final set that we're going to choose as the limit as n tends to infinity of these sets. And you just want that to be well defined. So in the first case, because if a point is added in some step, it is there. And if it's not there in a later step, then it's not there. So it's clearly well defined whether a point is in S infinity or not. But in the second case, this point, even if it's added to one of these sets, it can be removed at a later point. So like you can just add it, remove it, maybe add it again at some point. That's all very possible. So S infinity is actually not well defined in this case. So the solution does not work. Does that make sense? Okay, I'll assume you all are smart people and somehow understood everything perfectly. Okay, it's the reason I wanted to do this is because of a sad story. Let me find this problem. So this thing exists. To those of you who have been seeing ISL, yes, this is 2021 C6. No, I'm actually not spoiling the solution to this. It's a really nice problem. But I am going to point out a fake solve to this problem. So for context, this came on the IMO mocks, and I fake solved this with a thing very similar to the fake solve for the above problem.
Can you give a minute to read the problem?
Yes, of course. Is this problem hard? Yes, but we're not actually solving the problem. We're just discussing a fake solve and figuring out why it's a fake solve.
Why can't the rabbit move like there are infinite cells? Like why
Rabbit can't go to a cell it went before, so like if it went like this, it's now stuck in this thing.
Oh, I see.
So
like why will the rabbit go at such a
I mean, like if you think about it, then the rabbit doesn't want to give out much information to the hunter, so it would like to just stay in a small place and not move much. So this condition is preventing that because it says a rabbit must always move.
I see.
So you can't confine yourself to any fixed region. My most convincing fix. Yes.
What
I
did
think
you
this
do?
is more convincing. Can you show the previous problem? So the previous problem was, I'm assuming you mean this. You're given a set L of lattice lines passing through at least two lattice points. And you want to show that there exists a set P of lattice points such that for all lines L that belong to L, there are exactly 22 points of P on L. Wait, I think the actual problem just said like every lattice line has 22. This is just unnecessary. It's fine. No, the bio I will not show Lamar Revenge P6. That is not related to infinite stuff. I'll show it after the class ends or something. So essentially there you have the infinite square grid, like the plane, and the hunter just like colors every cell with finitely many colors. He needs finitely, otherwise if he does infinitely many colors, he'll just easily win. So the rabbit just like, moves around. It can move only to an orthogonally adjacent cell and stuff. And every time it announces what the color of the cell it's on. And the hunter wants to figure out if he can see where the rabbit started its long and arduous journey from. So yeah, this is quite an interesting problem. So the proposed fake solve is this. So first, because there are finitely many colors and infinitely many cells, there exists a color C1, right? That appears infinitely often. Like there exists some color that appears infinitely often, we'll call it C1. Next, we look at all possible occurrences of C1, right? So there we have infinitely many, and we're only going to consider the cells to the right of it. And this, you just have like C1, C1, C1. Like imagine in the plane you have like maybe this cell is C1, this is C1, this is also C1. The point is you have infinitely many. And we're going to look at the cell just right of that. So obviously,
we
because
look
we had
at what?
the cell immediately to the right of every occurrence of C1.
C1 is the color with rabbits at first.
No, the rabbit is not even involved. I'm just creating this thing for now.
Great.
Yes, so C1 is just a color that appears infinitely often, which exists by PHP because finite colors and infinite grid. So among all these second occurrences of things, again by PHP, there is a color C2 that again appears infinitely often. So the thing C1, C2 appears infinitely often. So now consider all the infinite occurrences of C1, C2 and consider the cell immediately after C2 there. And again by PHP, you can find a color C3, also C1 and C2 might even be the same, that's fine. I'm not saying they're distinct. So that C1, C2, C3, this kind of string also appears infinitely often. And then we can do the same thing, C1, C2, C3, C4 appears infinitely often. And you can just keep doing this. So now you have two infinite paths such that they all have the same color. So if the rabbit pretends to start on any of those two squares and just keeps moving right all the time, the hunter cannot figure out where it began. Because there are two different paths which start at two different squares, but they have the identical thing. And therefore the rabbit wins. So your job is to figure out why the solution is wrong, if it is wrong.
You said that if rabbit says right all the time,
The rabbit what?
rabbit goes right every time, right?
Yes.
So like in that case, so like if you go like, can you show your grid?
If you go what?
Can you show your grid once? No, like the red one.
What?
The red grid where you
What
drew
is the
that.
red?
Yes. So like C1, C2, C3, C4, so on will continue.
Yeah.
Like
What?
it is continuing two times, right? So like, that's not possible, no?
What? Like there's one that goes here, one here, one here. Why can't it happen?
And the coloring is C1, C2, C3, C4 in all of them.
Yes, like I've shown that such a thing exists by induction.
Let's see. Can it even exist?
Can you what?
Can it exist?
Can what exist?
This thing, like two sequences, same sequence.
Like maybe that's for you to figure out. I just told you my solution. Find out
Like,
if it's right or wrong.
if this exists, then sure, rabbit will win. That seems believable. But like,
I mean, I just proved it exists. No?
like you prove C1, C2 appear infinitely often, two colors.
Then by the same logic, it actually extends. That I promise is correct. Like consider all occurrences of C1, C2 and consider the thing right to it. You can have infinitely many things, finitely many colors. So
Oh,
some
right.
C3 occurs infinitely.
Okay. And so like then you say that rabbit can bet any of the C1, like any of the two, like there are two same sequences. So like rabbit is at one of them.
Yeah, the rabbit could have started at any one of them and he's telling the hunter the same thing. So the hunter can't really differentiate between them.
Also like that sequence will have infinite appearances through this induction thing, right?
Yes, but we just need to. Also, I did manage to successfully trick other people into believing this was the correct solution. Like after the mock.
So did you get 7 or 0?
0. Like I can't pull Archie. Like I was happy Archie did not kick me out or something because I left like 2.5 hours early or something. Because I thought I was done.
Oh, so like who believed that this was correct other than RG?
The other contestants.
Oh,
Like apart from Pranjal. Because Pranjal actually solved the problem. The others didn't. So
ah,
they thought maybe I was good. I assume it's because they're thinking. The class is not over. And also the class has been extended by 20 minutes or whatever because it started 20 minutes late.
Like if that coloring part is true, then I think your solution is correct only, no?
Yes. One more person I have tricked.
Like you can claim you have tricked 10 more people who all are in the meet. Like assume half of them are listening accurate list, like 5
There's
more.
one person I know who didn't fall for it, but he's not here. That is sad.
Like Rohan and Pranjal, right?
No, another person I told you after.
Krupar?
So someone asked this, so I will just repeat the solution. I assume you've seen the problem. Have you seen the problem? Okay. Just a second.
Pranav, are you there?
The class is going on.
Yes. Can you explain the question if that's possible?
So like there's an infinite grid and like n square cross n square grid. No.
And
Yeah, like
then
there is a grid like
Hello, what happened?
infinite.
N
yeah,
square,
okay, you were not there. So she's asking the explanation of question.
N
It's
square
Z
cross N square grid.
No, not n square. I mean z square cross z. Z cross z.
into Z. It's
That's-
okay.
XY
Okay.
plane.
Yes.
Oh,
So yes, you have an infinite square grid
Hmm.
that looks like this, extended in both directions. The hunter picks some number of finite colors, a finite number of colors, and every cell he just colors whatever he feels like, maybe like this. C5, C4, C1. So he just has this coloring that he does. And then the
okay,
rabbit, the color is what?
the number of colors are finite.
Yes,
Like,
otherwise you can just give every cell a different color.
Ah. Hmm.
So the rabbit starts at some cell, and then every minute, what does it say? Yes, every minute, the rabbit moves to an adjacent cell, but it can't visit any cell it has before. And the hunter, and every minute it also just tells the hunter which the color of the cell it's on. And the hunter wants to see if he can figure out where the rabbit began moving. Because that would also tell him where the rabbit is right now. And then he can like shoot and eat the rabbit or something. I don't know. Whatever his intentions are. Maybe he wants to keep the rabbit as a pet. So, oh yes, I will not get distracted. So, the solution, the claimed solution is this. Because there are finitely many colors in infinitely many cells, there is a color C1 that appears infinitely often. Do you agree?
Yes.
So we consider all these infinite occurrences of C1, like say here, 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 here. You get the point. And we consider the color just to the right of it. Because these are infinite occurrences and finitely many colors, there is some color C2 such that C1, C2 appears infinitely often. Do you agree? Like C1 and then C2 to the right of C1. Like there are infinitely many pairs and you have like C choose 2 ways to choose. So it has to be finite. And so you some C1, C2 appears infinitely often. And then once you have like these bunch of C1, C2 somewhere in the plane, you consider the things to the right of those. And again, by PHP, you can find a color that appears infinitely often there also. And you can keep repeating this. So you can get a C1, C2, C3, C4 appearing infinitely often, and so on. So eventually you get like two infinite paths, or you get infinitely many, actually infinite paths, starting at like C1 and having the same thing to the right. Do you agree?
I lost the track. Wait, C1 appears finitely.
C1 appears infinitely many times.
Oh. So C1,
Try
C2
right
appears
finite.
in.
It says infinite.
Ah,
Yes. So
complete the whole tradition. Wait,
sorry.
nothing. Just go on. So,
So
like
yes,
which?
because C1 appears infinitely often, you consider the cell to the right of it. So C1, C2 appears infinitely often.
Hmm.
And because finitely many colors and you have infinite occurrences, then again you can repeat same thing to show that C1, C2, C3 appears infinitely often. Then C1, C2, C3, C4. And like this, you eventually get like, you can get like at least two infinite paths starting at a C1 and then having the exact same thing to the right. So if the rabbit started at either of these points, here or here, and just kept moving right all the time,
The hunter won't be able to like find out which
what?
where like the hunter won't be able to figure out where the rabbit is by
Yeah, because the
the
rabbit is giving the same colors for wherever. So the hunter can't be sure of where the rabbit started. That is the claim proof that the rabbit wins. And so hunter does not have a winning strategy.
see.
But the proof is wrong.
Hmm.
Okay, suppose at any point of time, oh yeah, they are infinite sequences. That won't work.
Yes. The induction works. Like this is like one line of the proof that's wrong.
The C1, C2 one thing.
No, this is fine.
Pakka?
Like I promise this is true. This is also true. This is also true.
It's not true infinitely often. Like,
Yes. It's not exactly often.
like it's not true for the whole sequence is same.
Yes, you can get arbitrarily large lengths of path that appear infinitely often, but you cannot find two infinite paths that are the same always. Like if the hunter is just stupid and does some periodic colorings, then you can do that. But if the hunter is actually smart, then this will actually not work. Because let's use similar logic to what we were doing previously. Let's say S1 is the set of all possible starting points with C1. Then say S2 is all the starting points with C1, C2. Then S3 is everything with C1, C2, C3. So in this case, we actually have that S2 is a subset of S1, is a subset of S3, is a subset of S4, and so on. So because everything is a subset of the previous thing, S infinity exists. Or does it?
Like clearly it cannot be the S1, like Si cannot be equal to Sj. Clearly, the hunter can color like that.
You can.
Like the hunter is coloring, right? He'll do coloring such that Si is not equal to Sj.
Sure.
So at every point of time, the number of elements reduce.
It's an infinite number. How are you defining reducing? Like I agree, it does reduce, but it's still infinite. So the point is, we are claiming that if you have an infinite sequence of sets such that this is true, then I'm saying that there are like two elements in every SI. Because that's what I'm claiming, because I want infinite paths. But the problem is this is not true. Like S infinity can be empty. Consider this. let Si be the set I plus 1, I plus 2, I plus 3, and so on until infinity. So in this case, it is true. Each Si plus 1 is a subset of Si, and in fact, a strict subset, like a proper subset. So although we do have the same thing as above here, but the problem is there is no element that's in every Si, because any natural number you pick, beyond a point, it'll just drop off.
Oh, can you repeat the last name what you just said?
Any natural number you pick, say like 100, it won't exist in S101, 102, and so on. So like there is no natural number that appears in every of these sets. So actually like S infinity exists, but it's just empty.
Okay, this sounds dumb, but like if S infinity exists, S infinity plus 1, like how do I say? There exists something after that also, right?
Like S infinity is not an actual thing. I'm defining it as the limit of
Okay.
the Si.
Yes.
So like, and I'm assuming the limit is well defined, and the limit is well defined because of this. Because if an element drops off, then it can't ever come back. Because every succeeding set has to be a subset of the previous one. So like whether it's there or not, that's fixed. But the problem is, it's just possible that it can never be there. And in fact, this to convince yourself, consider this coloring. We'll just consider two colors C0 and C1. Okay, let's say colors X and Y. Then consider the coloring X, Y, X, X, Y, X, 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 Y, X, 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 Y, and so on. So suppose we picked C1 to be the color X, right? So we know that X occurs infinitely often. We know that XX occurs infinitely often. We know that XXX also occurs infinitely often. And for any number of n's, any number n, we have that x n times also appears infinitely often. But the problem is an infinite sequence of continuous x's never exists in this number. You can just show it for all arbitrarily large things, but an infinite thing you can never have. And that is the reason the solution fails.
Oh wait, how does this show that it fails?
Because what I was claiming was there are at least two infinite paths with all x. That's not even one.
I didn't understand the last one.
Which part?
This part, like what you were not claiming that there are infinite x, right? You were just claiming that there are two infinite same sequences.
Yes, this does not have two infinite same sequences.
Oh, I see. Also, the thing you just did and the fix of it in some sense, does it just not finish the proof of the problem that Hunter has a winning strategy?
How?
Uh, so like, oh, does Hunter know that when the rabbit takes turn?
Directly, no.
Okay. Oh, so like, it finds out somehow.
I'm not spoiling the solution.
Oh, you just did, by the way, like by saying it directly. Okay.
There are other solutions that exist, probably. But yes, the essential idea is the hunter wants to create like a very non-periodic problem. But like it's not obvious because the rabbit doesn't even need to keep going right. He can go like up, down, left, right, and keep changing that also if he feels like. He or she. I'm not assuming. So yeah, this proof does not follow. And so I get 0. It's sad, but life goes on. Is it 10:20 already? Oh, I don't have time for the ducks problem.
You can extend if you want, and if people want to stay with that.
Okay, I'll probably go over this proof pretty quickly then. It's like not doing justice to the problem. We must all respect the power of ducks. But okay, so this is the problem. I think I sent the problem in OMC, I'll just copy paste. I apologize for extending this class, but if you want you can feel free to leave if it's too long. But this problem is too good to not do. So yes, it is a crazy sounding statement because it's not even obvious how you can ensure that even one duck guesses correctly. Yes, I agree. It's not like I would have guessed no to.
So this thing seems similar to like some of the initial problems you did.
It's similar to the norms,
Yeah,
but
the
it's
norms one.
actually a lot more complicated. Like ducks are even smarter than norms, actually.
I mean, like norms had infinite memory and infinite computation power.
Even
How do
ducks,
you, so like how do you define smarter?
you will see. The ducks have to do like even more stuff. Like apart from memory, the ducks also have to do more complicated stuff. Their norms were just like, oh, this is in this class, so we are done. Here, ducks will have to think more.
Also, I think that if we follow the class solution, it's possible that the ducks get 0. Correct,
No,
right? No,
I'll show you
because
the strategy, then you can decide.
no, not the correct answer. But I'm saying that the strategy with norms followed, because that thing only guaranteed that there are some finite number of norms which did not get correct, right?
Yes, in
But
this case, that finite one could be all 100 guessed wrong.
yeah,
That is-
so that's what I'm saying. So like if we follow that strategy, it won't work.
And I
Obviously.
don't think that would even work here because you have real numbers, which are uncountably many.
All right.
So it not probably fine, yeah. Yeah, I think it would have worked if there are infinitely many ducks. He may have, I do not know of it. If you're talking about the one where there's like 100 people and they each open 50 boxes, that is very different from this. So that problem is also very cool, though. Yeah, not related. Integrate 6 years. Maybe. I don't watch it. So unfortunately, I do not have the time to discuss the whole thing. So I'll just essentially just tell the solution and then you can like gape and wonder and I'll just suddenly leave the meeting and you'll all be confused. So what the ducks are going to do first, obviously they label the boxes B1, B2, B3 and so on. So first divide into 100 groups. First group has B1, B101, B201, B301. Next one has B2, B102, and so on. Basically, mod 100. These are done. So you have like these 100 groups. So once again, we will do the same thing as before. I won't repeat it, but yeah, like consider all infinite sequences of real numbers, define the equivalence relation, and then consider all equivalence classes, and by the axiom of choice, pick a representative from each of them. You can do this. So what we're going to do is the following. Also, let's define that f of a sequence is some other thing. F of S is the representative of the equivalence class that the sequence S is in, and this is well defined. We will also define a function G.
How do you define an equivalence class with reals?
It's the same thing. Like if they differ in finitely many places. Like it is uncountable, but there also the set was uncountable only because you took infinite sequence of naturals. So
Also, there are at-max 100 groups, right? Because it's possible that two of this BI mod 100 and J mod 100 are the same equivalent.
like I'm assuming I haven't opened any of the boxes. I am classifying the boxes, not the numbers that it.
No, aren't you doing like from each box to take a representative element?
No, I'm just like ignore what I said earlier. I'm just saying define this equivalence class. So now there is some function. So let G of S be the last place where S and F of S differ. Okay. And also let's call these sequence of boxes, I don't know, small b1, small b2, all the way till b100. So this what F and G is makes sense. I will assume so. So what the duck I will assume.
F again. I don't get F. F of S. I don't get the function F of S. Like, how is it?
So like define an equivalence class on infinite sequences of real numbers where two sequences are equivalent if they differ in at most finitely many places. This splits it into a bunch of equivalence classes. By the axiom of choice, you can pick an element from each equivalence class.
And it's F of S is not related to that B101 stuff.
It's not related. And I'm just like defining notation. That's what F is, and this is what G is. And G is finite because of how we defined our equivalence class. Does that make sense? Because beyond a point, they are all the same. So what duck I does, he opens B1, B100, like this B1. We defined it like this. He opens all of these boxes. He opens B2, like B2 is just the sequence of all those boxes, right? Or that's not a good idea. He opens all these boxes. $99, 100, B100, B200, and so on. So he opens every box except the boxes marked I mod 100. So he just opens every other box. I'm assuming that duck is male. Why not? So he opens every other box, right? And then he calls this sequence B1 the reals that he sees inside these boxes, right? And he calls the sequence of reals he gets here B2, and he calls this B100. So basically he knows all of B1, B2 until B100, but not bi, because he hasn't opened any of the things over here. Do you all agree? So now what he does is he finds a number n, which is defined as this. He finds this number. Like basically, he finds g of each of those 99 sequences he gets, and then he defines n to be one more than the maximum of all of those, so that n is bigger than all those maximas. Does that make sense?
G is that like the B of K and the last different place with its representative.
Yes,
right?
it's the last place at which s and f of s is different.
Is it the index or the value at that place?
The index.
Oh, the index of that.
Yeah, so all these are just natural numbers. So n is also a natural number, right? So now the duck comes back to this. He opens B 100k plus I if k is greater than n. So like in this sequence that he hadn't touched before, he skips the first n boxes and then opens all the remaining boxes. And then he guesses, and this is some sequence, say B, right? And then he finds f of B, and he guesses the nth place of f of B. So like just the box he didn't open, because he opens B 100k plus I if k is greater than that. And we claim this works.
Everything is fine. But
What?
I forgot what we had, what the ducks guess.
Oh, the ducks just guess some real number, and they guess correctly if on one of the unopened boxes, the real number is there.
So basically, they just have not opened a finite number of boxes, each duck.
Yes, in this case, yes.
In each case, basically.
In each case, yes. So the point is,
Wait, okay, sorry to disturb so much, but duck open B 100k plus I, and then it can guess like what f of B is, of course.
yes,
And what does it do after that?
it guesses the nth place of f of B.
Isn't n random?
No, I mean, n is well defined here.
Okay.
Like basically it skipped the first n boxes and opened everything afterwards. And it got some sequence f of B, right? So it guesses like this place of f of B. So the point is, if this duck got it wrong, also let's call this ni because these may vary for each duck. If this duck guesses wrong, it means that f of B and B and BI actually differ in nth position.
Oh, can I finish from now?
Yes.
That like now clearly nth will be the largest position because the others were smaller than that. It's like all the
Yes,
other 99
because
ducks will
basically
get split.
G of BI is at least this, at least n, because they differ in the nth position.
Yeah.
Greater than actually.
So like this is the largest thing. So for the other 99 ducks, when they guess that, it will be actually in that boxes.
Yes, because the way we defined ni, it is bigger than G of B k for all k not equal to I. So a duck guesses wrong only if G of Bi is strictly greater than all of the other ones. But this can be true for at most one n, I. Because if something is the maximum bigger than everything else, Like nothing else can be bigger than it. So yes, at most one duck guesses wrong. So at least 99 ducks guess correctly.
How do you think of this proof I have?
Like it kind of makes sense.
Yes, proof makes sense completely. But how do you think of this? It does not make sense.
Like the idea of defining the equivalence class is known because you know the other problem.
Yes.
And doing the same thing for reals is nothing different.
Like how do you define ni thing?
How do you
G?
define?
Like how do you motivate defining G? Okay, fine.
I
That's
mean,
also motivated.
G is just fine, like how far it differs. That's all you.
Yeah, but like n.
Like n is just contrived because essentially you want to leave only finitely many boxes. If you leave infinitely many boxes, you're probably not going to guess. So leaving these finitely many boxes, you want to guess correctly. But the problem is that the way the equivalence class is defined, all you know is that it differs in at most finitely many places. So if it differs, so you're not sure exactly at what point to like leave those boxes unopened because you're just not sure. And it's true, all 100 ducks just cannot guess correctly.
Yeah.
For obvious reasons, because you can just rig one duck to fail. But the point is, in this case, if you rig one duck to fail, everyone else wins. So basically, you want to make it such that, yeah, if one duck fails, then everyone else manages to do it. So if so basically ni, just don't define. Assume the duck just picks it randomly based on some intuition. So you know that g of bi is at least ni, right? So that's all you know. So if you manage to choose ni based on the other gi, then you can manage to rig it this way. Because all it's saying is that ni is bigger than any other gi. But yes, it's not obvious at all. It is quite tricky. And it's pretty clever too.
It was really nice though.
And with that disturbing and nice duck problem, I'll actually end the lecture. If there's like any questions, feel free to ask. I apologize for going over time. Although the initial delay was not my fault.
Yeah, I apologize for that. So shall I stop the recording?
Yeah.